In this session, we will build a logistic regression model using PyTorch. First, let's understand what a logistic regression is. In logistic regression, our model predicts the probability of a binary event occurring. A binary means something we can say yes, no, true, false, or 1, 0. So, logistic regression is a binary classification task. Let's look at an example of binary classification. Suppose we have data points where each point has two attributes, x1 and x2. Each point belongs to one of two classes. I used red and blue colors in the plot to indicate their respective classes. The question is, can we train a model to learn which class each data point belongs to? In other words, the model must predict the class of each data point, given x1 and x2 attributes. Visually speaking, the model must predict from the left graph to the right graph. Let's formalize the binary classification task using numbers instead of plots and colors. Let's label blue points as class 1 and red as class 0, so we can use 1 and 0 as label values. The input to the model is x1 and x2, and the model's output is p hat, the probability of the input data point belonging to 1. If the probability is more than 50%, the model predicts the data point is from class 1. Otherwise, the data point is from class 0. To reiterate the point, the input to the model is x1 and x2, and the output is p hat, which is the probability of the input data point belonging to 1. It also means the p hat is bounded between 0 and 1. Therefore, the model must ensure the output is between 0 and 1. Then, we can check whether the probability is more than 50% and see if the data point is from class 1 or 0. Can we use a linear regression model to perform the logistic regression task? Let's see. As we feed two input values to a linear regression model, we need two weight values and one bias value. It's simple matrix multiplication and addition. We can use PyTorch's NN linear module to handle the calculation. However, there is a problem. Since x1 and x2 can be any values, output z is unbounded, meaning it can be anywhere between negative and positive infinity. Then, how can we tell what value of z means class 1 or otherwise? We seem to hit a wall here. Is there any way that I can convert z to probability? So, the problem is that probability must be bounded between 0 and 1, while a linear model can output any value. Therefore, we must somehow map output z to probability. Or, we can think of a way to map from probability to unbounded value. For example, a higher probability should map to a larger value towards positive infinity. First, we can think of the odds of class 1, which is the ratio of the probability of class 1 over not class 1. Not class 1 means class 0 in our example, and class 1 probability is p, and class 0 is 1 minus p. So the odds of class 1 is p over 1 minus p. If the probability of class 1 is higher, the odds value is larger towards positive infinity. The transformation from probability to the odds is monotonic, meaning the odds increases as the probability increases. The reverse is true in that the probability increases as the odds increases. Therefore, we can convert between the odds and probability. However, the odds value ranges between 0 and positive infinity, whereas z can range between negative and positive infinity. We need one more step to map from probability to unbounded value. We take the log of the odds, which we call logit. the resulting value can range between negative and positive infinity. The log here is the natural logarithm. This transformation is also monotonic. So, the larger the odds, the larger the logit, and the smaller the odds, the smaller the logit. Therefore, we can map from probability to odds, and odds to logit. We can also go from logit to odds to probability. As such, the larger the probability, the larger the logit towards positive infinity. And the smaller the probability, the smaller the logit towards negative infinity. Also, when the probability is 50%, logit is 0. We want to convert the linear model's output z to probability p. So, we say output z is a logit, which is an unbounded value. The logit is the log of the odds, and the odds is p over 1 minus p. Now, we have an equation between linear model output z and the probability of class 1, p. We can take the exponential on both sides and then rearrange the equation. Finally, we can calculate probability from output z. We call this function sigmoid. We often use the sigma symbol for it. Sigmoid maps any unbounded value to a probability between 0 and 1. It is a smooth continuous function, and we can calculate partial derivatives. So, we can include it in a computational graph to perform backpropagation. PyTorch provides NN sigmoid as a module that we can use in our model. A logistic regression model is a linear model plus the sigmoid. Our model takes input x, performs the linear operation, and applies the sigmoid function. The output is an estimated probability of x belonging to class 1. If the probability is more than 50%, the model classifies input x as class 1. Otherwise, class 0. Using the sigmoid function, we can use a linear model to predict the binary classification. Now, the question is how to train this model. What should be our objective for binary classification? Our target label y is either 1 or 0, while our prediction is an estimated class 1 probability between 0 and 1. So, we want p hat to be higher when y is 1, and p hat to be lower when y is 0. In other words, we want 1 minus p hat to be higher when y is 0. We can combine these two into one function called Bernoulli probability. Bernoulli probability becomes p hat when y is 1, and 1 minus p hat when y is 0. We want to maximize this function as close as possible to 1. So, we want to maximize the Bernoulli probability. If we have two data points, we'll have two Bernoulli probabilities. To calculate the joint probability for the two data points, we multiply them. Here, we assume each data point is independent because one data point belonging to class 1 does not affect other data points. The classification of each data point should only depend on the data point and nothing else. Hence, the joint probability is the multiplication of independent probabilities. We need to multiply all three if we have the third data point. If we have 10 data points, then we multiply them all. However, multiplying values less than 1 many times would result in a very small number, which is troublesome since computers have limitations in how much precision they can maintain. Instead, we apply the natural logarithm to it, then multiplication becomes additions where we apply the log to each Bernoulli probability. Moreover, the log to each Bernoulli transforms the multiplication within the Bernoulli probability into additions. We want to maximize log Bernoulli probabilities for all data points. In machine learning, we think of minimizing loss. So, we want to minimize negative log Bernoulli probabilities for all data points. In other words, we want to minimize the mean of negative log Bernoulli probabilities. We call this binary cross-entropy loss. Now that we have our loss function, we are ready to write a training loop with PyTorch to train our logistic regression model. To summarize, logistic regression is still a linear algorithm, as it assumes a linear relationship between input and logit output. We apply sigmoid to convert logit to probability. Sigmoid is also called the logistic function. We want to train our model to predict correct classes by maximizing the Bernoulli probabilities. We minimize the mean of negative log Bernoulli probabilities, which we call binary cross-entropy loss. And PyTorch provides a module to calculate binary cross-entropy loss, so we do not need to deal directly with log probabilities. But it's good to know what's happening under the hood. That's it for this video. I hope you enjoy learning how logistic regression works. Bye for now.